Now, let us look at the divide and conquer strategy in this session. Now, this is the one of the topic of the second unit. In this topic, we try to solve a computational problem using a divide and conquer approach. Now, this is one of the approaches of solving a computational problem. A divide and conquer approach, or the strategy what we call, apart from the other strategies, this strategy uses a different kind of technique to evaluate and to compute or solve a problem. Now, as the name suggests, the divide and conquer approach, what we have is, we have a problem which is large. A large problem, let us call this problem as P. As the name suggests, divide and conquer, let us first try to look at what is divide. When the problem is very large, the problem is divided into sub-problems. Like, for example, if we have a problem P, the problem P is divided into sub-problems P1, P2, P3, so and so till K sub-problems. Now remember that when we call this problem and we say that it is divided into sub-problems, the sub-problems also should be of the same nature or same type. For example, if we have a problem, a large problem of finding from a collection of elements, finding which one is minimum and which one is maximum. So problem P1, P2, P3, that is the problem P is divided into P1, P2, P3, and these problems should be of the same type. P1 also should find from a small collection minimum and maximum. P2 should also find from a small collection minimum and maximum. So problems P1, P2, P3 are also problems of finding minimum and maximum. Now, these problems of finding minimum maximum is just an example. Let us take another example. Suppose if we have a problem P of sorting a collection of elements. So even P1, P2, P3 should also be sorting problems. They cannot be a different problem. For example, if I have P as a sorting problem, P1, P2, P3 and until Pk sub-problems, when we divide this problem, this P1, P2 should not be finding maximum element. Sorting means the problem, the entire set has to perform sorting itself. And one more important point is that these sub-problems, P1, P2, P3, whatever we have, we divide that. These sub-problems are non-overlapping. They do not overlap. For example, if I have a set of elements from 1 to 10, if I divide those elements from 1 to 5, so P1 will have 1 to 5, P2 will have 6 to 10. So they are non-overlapping problems. Now, what we have is, when we divide a problem into different sub-problems, what we have is what we say, conquer, is nothing but, we say that each problem, sub-problem, P1, P2, a small problem can be solved easily. So a large problem is divided into small problems, sub-problems, and each small sub-problem can be easily solved. So S1 is nothing but a solution to sub-problem P1. S2 is solution to sub-problem P2. Same way we have solutions for each sub-problems. Then the conquer part is when we have the solution to each of the sub-problems, we combine these sub-solutions, what we call, and we combine these sub-solutions to get the solution to the original problem P. So here P is the original problem, which is divided into P1, P2, P3, P till Pk, that those are sub-problems. Each problem can individually be solved easily, and those solutions are as sub-solutions, what we call as S1, S2, S3 till Sk, and they are combined to get a solution as S to the original problem. Now suppose when we divide a problem P into a sub-problem P1, that sub-problem P1 can also, or sub-problem P2, P3 can also be large problem. So they can in turn be divided. So P, problem P1 subproblem can, if it is large, can in turn be divided into subproblem, and their solutions can be found. Then those solutions are combined to get those sub solutions are combined to get a solution to S1, and finally we get the solution to the entire problem or the original problem. So here in this case, if you look at this part, that is the sub-problems, this part is divide part. And then when we have the solutions for this divide, we combine the solutions, that is we are performing the conquer approach, and that combining the solutions will give us the original solution. So this is what is the basics, or a basic theory about how divide and conquer approach works or strategy works. Now, obviously, every problem has its, to solve any problem, we have to have an algorithm. The same way, for divide and conquer approach, we have a general algorithm. Let us call this algorithm as D and C for divide and conquer, and P, we are passing parameter as P. P is nothing but a problem, a large problem. Now, once this divide and conquer approach, the algorithm is called, the very first thing we check is if the problem P is small. If the problem P is small, that means we can easily find the solution. That is, S is the solution here for the problem P, and we return this solution S. Now else, if the problem is large, if the problem P is large, then we divide the problem. Remember that this is not specific. This is not specific to sorting or finding minimum, maximum, or merge sort, or any other application what we have. This is the general algorithm. So we divide P into smaller instances or subproblems, that is P1, P2 till K, where K is greater than or equal to 1. Obviously, when we are dividing, it has to be greater than or equal to 1. Then we apply divide and conquer approach to each of these subproblems. Which subproblems? P1, P2, till Pk. Now remember here, we say we are applying divide and conquer. So what does this mean? This means that it will be a recursive algorithm. This is going to be a recursive algorithm. So we apply divide and conquer to each of the subproblems. So this is P1 is again passed to divide and conquer. So instead of P, we have P1 here. Then if P1 is small, then we have the solution for P1. Else, again we try to divide P1. Over here we will have P1 into small instances like P11, P12, P13, and so on, P1K. Now, once this recursive call is made, even P2 will have its recursive call till Pk. Then once we have the solutions, that is S of P, we combine those solutions. So this is combine those solutions of divide and conquer of P1, divide and conquer of P2 till Pk. So this will give us the problem, for a solution for this problem, a large problem P. Now remember here, this algorithm is a general algorithm for divide and conquer. It is also known as control abstraction. Sometimes the textbook uses this word as control abstraction for divide and conquer approach. What we mean by control abstraction is that this algorithm, divide and conquer, just gives us the general idea of how to do it. It doesn't describe what small function does, what is the S function, that is the solution function, then how to divide those instances, P1, P2, P3, and how to, obviously this is a recursive call, so it will be same, and how to combine. So this functions what are used here, small, solution, combine, all these are abstract functions. These functions do not tell us what to do and how it is done. It just tells about that this is how an algorithm should work. So that is why we say abstraction. It's very abstractly it is defined. That we have a problem as a small problem, then get the solution. Combine or divide the large problem into different problems, then recursively call, and then combine those results. So they don't specify specifics. They don't give the specifics about how to solve that problem. And those specifics depends upon each and every problem where we can apply divide and conquer approach. That is why it's called control abstraction. So this is what is a general algorithm for divide and conquer. Now, divide and conquer approach or strategy can be applied in binary search. This term you might be familiar with. Can be applied for finding minimum maximum elements from a collection of elements. Can be applied on merge sort. You might be familiar with this merge sort term. Quick sort, one of the sorting techniques, and merge sort and quick sort are the most efficient techniques of sorting a collection of elements. And it can be applied in selection problem. That is, here finding maximum and minimum elements is nothing but the same problem which we apply for the selection. That is, instead of finding maximum, minimum, we try to find in selection the kth maximum or kth minimum element. And then Strasson's matrix multiplication, the same divide and conquer approach is applied. Matrix multiplication you might be familiar with, which has several operations of multiplication and addition. Strasson's uses a different approach, gives us the way or tells us the way how to apply how to multiply a large matrix. Then we have convex hull. This is one of the geometric problem that can be solved using divide and conquer approach. So these are the different problems that can be solved using divide and conquer approach. Now we will look at each of them in this the complete what do we call this unit. One of the part of this unit is that. Now before we move on to computing, to apply divide and conquer approach on different problems like binary search or sorting, so and so. Let us first look at how to find the time complexity, because this is one of the major things why we design an algorithm. We have to design an algorithm keeping in view or having the complexities into consideration, and we need to have an efficient algorithm, or we need to devise an efficient algorithm. So here, let us look at how to find or how we can compute the complexity or performance of a divide and conquer algorithm. Again, if you see, we are using the control abstraction here. We abstract divide and conquer algorithm we are using. We are not talking about any specific problem. Now here, if you see, the problem is P. The problem is of size n. That is n number of elements, what we call. That is the input, initial input for the problem. Now let us assume that divide and conquer approach uses or takes Tn time. T is time function. Like we have seen in the earlier classes that the computation of an algorithm is expressed in terms of functions, and depending upon what polynomial that function is, we try to say that the function takes O of n time or of O n square time, cubic or logarithmic or polynomial time. So let us assume that this divide and conquer algorithm takes T of n as the time. Now, if the problem P is small, obviously this is a primitive statement, it will return the solution to that problem. Now, we have already said, or in the earlier classes talked that primitive function, said that the primitive statements will take unit of time. The same way, if it's a primitive statement, so it takes unit of time, because unit of time is constant, we can ignore that. Return statement also takes a primitive time, but here S is a function which gives us the solution for the problem P. So we don't know what this S function is going to take, how much time it is going to take. So that is why we don't say that it takes primitive time, though it says return statement. Let us say that it takes G of n time. some function g of n time to give the solution. Then obviously else is also a primitive statement. Now here, dividing a problem P into small instances, even this might be a primitive statement, but let us say that this statement, or dividing a collection of elements, will take a time of f of n. So we are trying to represent the entire algorithm of divide and conquer, general algorithm for divide and conquer, using different functions. So let us assume that the divide function, the divide process of dividing a problem into subproblems will take f of n as the time. Then this function, this statement, apply divide and conquer to each of these subproblems. This is a recursive function. Applying divide and conquer, you are recursively calling it. So when you are recursively calling it, suppose P1, subproblem P1 has got N1 as the number of elements, or the size is N1 for P1, N2 for P2. So what is happening is, you can see P is size N. So recursively is P1 is called. This one we are saying, assuming it's N1 is the size of subproblem P1. So P will now be N1. So when we call this, what happens is, since divide and conquer takes T of n as the time, and this is a recursive function, so the first part will be taking, the first subproblem P1 will be taking T of N1. Then again recursive call is made to P2, so it will take T of N2. Assume that P2 has the size is N2. And so on till Pk, that is so on till T of Nk. Now this one is summation, because every time divide and conquer is called for each and every subproblem. So for each and every subproblem, this statement will be taking T of N1 plus T of N2 plus T of Nk as the time. That is the summation of the time for calling the divide and conquer for each subproblem. Then we have the return function, returning the combined one. This is a primitive statement. Return combine. Combine whatever solutions we have, we combine those solutions. So the entire algorithm, we have the time taken by the entire algorithm of divide and conquer, that is Tn. Tn will be equal to sum of Gn plus Fn plus Tn plus Tn2 plus Tn Tk. But here, what we have is G of this f of n and t of n and summation part will work if the problem is large, and return solution will work if the problem is small. So if problem is small, we have g of n. So here if you see, we have g of n if n is small. If n is small. And otherwise, if n is large, whatever problem is large, it will be summation of T1 plus T2, or T of N1 plus T of N2 plus T of N3 till T of Nk plus F of N. So we will have plus F of N. So this forms the recurrence relation. Recurrence because we are recursively calling the function. So this T of N forms the recurrence relation for this divide and conquer approach. And always remember that the time complexity of the recursive algorithms are always computed using recurrence relation. Other algorithms, iterative and all, you will simply have the statements, you sum up those statements, and whatever polynomial you get, that will be the time complexity of that function. But for recursive algorithms, we will be using recurrence relation to compute its complexity or time complexity. Now let us look at this. So here the generalized form of this problem. What we have over here is T of n. That is the time function. Same recurrence relation we have g of n if n is small, and so T of n1 plus T of n1 plus T of n2 so and so plus T of f of n is otherwise. Now what we generalize, or what we say in general terms, is that this g of n is the time taken when n is small. We consider that n is the size of the input, and we consider that when the size of the input is small, means we say n is 1. So when n is 1, we say that the size of the input is very small, or the size of the problem is very small, and we can easily solve that problem. In And when we say we can easily solve that problem, that means it will take unit time to solve that problem. So what happens is we can rewrite this T of n function, recurrence relation T of n equal to, when n is small means when n is equal to 1. So when n is 1, g of n, we say that it takes unit of time. What is that unit of time? It's T of 1. So when n is 1, so we say it's T of 1. Then otherwise means if n is greater than 1, if n is greater than 1, that greater than 1, we try to divide this n1 plus n2 plus n3, obviously it's T of n, but we say that n1, n2, n3 is nothing but equally divided by some constant. So n1, n2, n3 will be n by 2, n by b, n by b, n by b, which is nothing but b is some constant. So summing up all these things, n1 is n by b, n2 is also n by b, n3 is also n by b, some constant b. We are trying to divide this problem using some constant b. So all these are summed up, and let us say they are a times we have the call to the recursive function. So T of whatever, T of whatever, T of whatever is a times. So we can rewrite this entire thing as a multiplied by T of n by b, where n by b is nothing but n1, n2. So every sub-problem, the size of every sub-problem, n1, n2, n3 is n by b plus the remaining f of n, which is plus f of n over here. So this becomes the generalized form or reduced form for the recurrence relation of divide and conquer approach, where a and b are constants and f of n is the time taken by a function to perform the dividing approach, the time taken for dividing. And when n is equal to 1, the problem is small, which takes unit of time, that is T of 1. Now here, there is one more thing we need to remember, that when we are saying the input n is divided by some constant b, we generally assume that this n is b power k. B power k is nothing but k is the number of sub-problems. So it's b power the number of sub-problems, which is n. So generally we say that this is going to be some kind of, we try to usually we take b as 2. So when we take b as 2, so 2 means dividing every time by 2. If an array is there, we try to divide it by 2, again half, again half, again half. So 2 power k means if k is 8, that means, if let's say k is, let's say 4, 16, n will be 16. So 16 number of elements are divided into 4 sub-problems. So that is what it means. So this is the general form of the recurrence relation. And we have to solve this recurrence relation, and obviously solving the recurrence relation, we will try to look at each recurrence relation when we look at the problem itself. So this was the general form of recurrence relations for divide and conquer approach. Now, so we're going to take up recurrence relation for each problem, and which uses divide and conquer strategy, and then we will try to solve that recurrence relation and find out what is the time complexity of those algorithms or those applications.